Today, we will start with the second major topic in the syllabus, namely heat conduction. Now, more specifically, I should say, we will be talking about heat conduction in solids. We will be concerned with trying to find the temperature distribution in a solid for certain situations, trying to find the rate at which heat flows in and out of solids given certain specified conditions, either in the steady state or in the unsteady state. One reason why we study heat conduction in solids first is that of the three fundamental laws, the law of conservation of mass and Newton's second law of motion are trivially satisfied when we talk of a closed system within a solid. We do not have to worry about mass being conserved, obviously, it is trivially satisfied, and Newton's second law of motion is concerned with force and momentum. That too inside a solid is not of concern to us. It is like saying almost 0 is equal to 0 or something like that. What we need to satisfy is only the first law of thermodynamics, and that too applied to a closed system. Now, in the first law, we say rate at which heat enters the system minus rate at which work is done by the system is equal to rate of change of energy of the system. Inside a solid, the work term does not exist. So, the first law simply reduces to the form dq dt equal to dE dt, because there is no work involved. So, this is one good reason why we study heat conduction in solids first. It is mathematically, shall we say, a little simpler in the sense that of the fundamental laws we have to satisfy only one, and that too the first law for a closed system. Now, what we are going to do is, first of all, in order to get a little familiar with the situation of heat conduction, we are going to consider a number of one dimensional steady state situations. Steady state means the temperature does not vary with time, and one dimensional means the temperature varies only in one direction. The first situation which we are going to consider is that of an infinite slab. Let us say I have a slab of width b, its two faces, the one on the left is at a temperature T1, the one on the right is at a temperature T2, is maintained at that temperature T2. The thermal conductivity of this slab, let us say, is K, small k. We would like to find out by conduction what is the rate at which heat flows across this solid and what is the temperature distribution in the solid. By conduction, obviously, heat has to flow in the direction of decreasing temperature. So, if I assume T1 to be greater than T2, the heat is going to flow from left to right, something like this, across the slab, all right, like this, all right. And I would like to derive an expression for the rate at which heat flows across this slab. I would like to derive an expression for the temperature distribution in this slab. That is what I am trying to do, all right. The way I will proceed is, of course, to use Fourier's law of heat conduction and the first law. These are our basic tools for solving the problem. So, let us first of all now see that suppose we want to use these. So, I have already made a statement that the flow of heat is one dimensional. I have already made a statement that the flow of heat is one dimensional. Let me write that down. One dimensional. All right. And therefore, and its steady state, therefore, the temperature in the slab will only be a function of one direction, and we will call that the x direction. All right. Therefore, since temperature is only a function of the x direction, it follows that Fourier's law can be stated as q by a is equal to minus k dt dr dt dx sorry dt dx. Notice I am using an ordinary differential, not a partial differential. Why? Because t is only a function of x. Now, the first thing I am going to do is I am going to use the first law of thermodynamics first of all to show that the quantity q, the rate at which heat is flowing across the slab, so many watts, is a constant. And I do that as follows. I say, all right, suppose I take a slab. Let me just draw a slab here. Suppose I draw a slab. This is a slab. All right. And let us say at some distance x from the left face, some distance x, I consider a plane x at a distance x. Now, also consider another plane which I will show in a slightly different manner at a distance x plus dx. Let us say a second plane at a distance x plus dx, like this. All right. This is the plane x and this is the plane x plus dx. Now, consider heat flowing across this slab through the planes x and then through the plane x plus dx. The heat is flowing at the rate q. Now, if the quantity q flowing across x, some area of x, is not the same as the quantity q flowing across x plus dx, if it is not the same, then the first law of thermodynamics says that the temperature of the slab, the energy of the material within these two planes x and x plus dx will have to increase, either increase or decrease, will have to change if q is not the same. And if that happens, the temperature will have to change. But we have already said that the temperature is not changing with respect to time. Therefore, it follows that q across any plane x, x plus dx or x plus 2 dx, whatever, any plane in this slab will have to be the same everywhere. So, q is a constant. That is what the first law, from the first law we have shown, q is a constant. All right. It follows, if q is a constant, that q by a is also a constant, because a, the area through which heat is flowing across this slab, is the same. It is a one dimensional situation, the heat is continuously flowing across the same area. So, if q is a constant, it follows q by a is a constant. So, using the first law of thermodynamics, we have shown q by a is a constant. Now, with that information, let me rewrite Fourier's law in the form, I will say q by a, which is a constant, into dx is equal to minus k into dt. All right. And let us integrate this expression. Let us integrate this expression between the limits from one end of the slab 0 to b, x equal to 0 to x equal to b, and the other one at x equal to 0 the temperature of the face is T1, at x equal to b the temperature is T2. So, integrate it, and once we integrate it, we will get the expression, we will get the following expression. If we integrate it, we get the expression q by a is equal to k by b into T1 minus T2. This is the expression for the rate at which heat flows across the slab. If I want the temperature distribution, we integrate the same earlier expression, but from 0 to x for x and from T1 to T for the variable T. And we will get the second expression which I have shown here, that for the temperature distribution, namely T1 minus T upon T1 minus T2 is equal to x by B, which is just a straight line, simply saying the temperature will vary in a straight line across the slab. Mind you, this is derived under the assumption that K is a constant at all points within the slab. All right, keep that in mind. If K is not a constant, then I will have to put that variation of K with temperature into account and put that variation into the integration. So, I will get a different answer in that case. So, this is with the assumption that K is a constant. So, these are our two results for the temperature distribution in the slab, which is a linear distribution, and heat flow rate across the slab. Now, we will solve the same problem for the cylindrical situation. Let us say I have an infinitely long hollow cylinder, all right, and it is of inner radius r I, its outer radius is r O, the inner circular face is maintained at a temperature T I, the outer is maintained at a temperature T O. Its thermal conductivity is again a constant, namely K. I would like to find, again like in the earlier case, to find first of all the temperature distribution, in the solid, and secondly to find the radial heat flow rate, all right, just like in the earlier case. The only change now is we have switched from a slab to a long hollow cylinder. So, we would like to find expressions for these, and we will proceed in more or less the same manner that we proceeded earlier for the slab, excepting that now we will be working with a one dimensional situation in cylindrical coordinates. So, what will we have? We will have, again, if you argue out, you can say it is a one dimensional situation. So, the temperature will only be a function of r, the radial direction. It will not be a function of theta or z or of time because it is not it is a steady state situation. Therefore, Fourier's law will yield q by A is equal to minus k dt dr, where the dt dr is an ordinary differential. And now, mind you, in a cylindrical situation, the area A across which heat is flowing is continuously increasing as we move outwards in the radial direction, unlike the infinite slab case. All right, you follow that. Therefore, for A, I will have to put q divided by 2 pi r L, where r is any radius within the cylinder, L is some length of the cylinder. Q divided by 2 pi r L is equal to minus k dt dr. And q is a constant, of course. Just like we had shown in the previous case, we can argue that q is a constant by using the first law of thermodynamics. Q has to be a constant. So, again integrate this expression. We write this as q upon 2 pi L, integrate it from r I to r O dr by r, all right, and that is equal to minus k, the integral T I to T O, the inner face to the outer face dt, all right. That is how we will integrate. So, rewrite the Fourier's law in this fashion, integrate from the inner face to the outer face, and after doing that, we will get the result for the temperature distribution and the heat flow rate. We will get the following. We will get for the heat flow rate Q is equal to 2 pi K L into T I minus T O upon the logarithm R O by R I, logarithm to the base E, and the temperature distribution would be T minus T I upon T O minus T I is equal to the logarithm R by R I upon the logarithm R O by R I. This would be the temperature distribution inside the cylinder. So, these are the corresponding results for a long hollow cylinder. Now, let us do a problem. We are going to do the following problem, numerical problem. I am going to say, let us do the following just to illustrate the use of the equation which we have just derived for heat flow rate. Let us say we have given a long hollow tube, given a long hollow tube. Let us say ID inner diameter 2 centimeter, outer diameter 4 centimeter. Okay. Let us say its thermal conductivity K is equal to 0.58 watts per meter Kelvin. Looking at this value 0.58, I hope you immediately recognize it is not a metal. Tube is made of some non-metallic material, say a plastic or something like that. And let us say the inner face, the inner circular face is maintained at a temperature of 70 degrees centigrade, and the outer is maintained at a temperature of 100 degrees centigrade. Okay. This is the given data. Find the value of Q by L, the heat flow rate per meter length of the tube. It is a direct substitution into the equation that we have just derived. Now, one good habit which I think you should get into is always draw a sketch of the physical situation that you are dealing with. Very often one can visualize it. It is a simple enough sketch, simple enough situation that you can visualize it, but still it is a good habit to always draw a sketch. So, in this case what will we get now? If I draw a sketch, it is going to look something like this. Let us say this is the outer surface, this is the inner surface, and let us say this is the center line. All right. So, the inner diameter is d I. So, I will have d I is equal to 2 centimeter, all right. DO is the outer diameter is equal to 4 centimeter. Okay. And this is my solid tube whose K is given to be K is equal to 0.58 watts per meter Kelvin. So, this is the solid tube. Okay. Now, the inner face is at a temperature of 70 degrees centigrade. This is T I. And the outer face is at a temperature of T O, is at a temperature of 100 degrees centigrade. All right. We would like to find the value of Q upon L. Heat is going to flow. we would like to find the value of Q by L, the rate at which heat flows in the radial direction. Mind you, you can see I am drawing the arrow always in the positive r direction. We would like to find Q by L for this situation. It is a straightforward substitution, there is no complications this problem. I just want to you to get into the habit of drawing a sketch, putting down the data and solving the problem. So, substitute into the equation we had. What was our expression? The expression we had was Q by L is equal to 2 pi k into T I minus T O, that is our expression, divided by the log to the base e R O by R I. So, in this case, substituting the data, we are going to get 2 pi 0.58 into 70 minus 100 divided by, this will be divided by the log to the base e 2 divided by 1. 2 centimeters is the outer radius, 1 centimeter is the inner radius. I do not have to put it in meters because I am dividing one by the other and it becomes dimensionless automatically. And this, if you calculate it, if you put in the numbers and calculate, you will get minus 157.7 watts per meter for a meter length of the tube. All right. So, that is the answer to the problem. It is a direct substitution into the formula which we just derived. And what is the meaning of this negative sign? Please note it. The negative sign is because in this case the heat is flowing in the negative r direction. The positive r direction is outwards. Since the outer face is at a higher temperature compared to the inner face, the heat flow is actually inwards. Therefore, we are getting a negative sign. All right, that is the meaning of the negative sign. Okay. So, now we have expressions for two one dimensional situations, a slab and a cylinder. What I would like you to do on your own is the following. I would like you to do the problem that I just solved, do the problem with the same data for a hollow sphere. Repeat this problem. That means, assume you have got a hollow sphere, inner diameter 2 centimeters, outer diameter 4 centimeters, inner face maintained at the temperature of 100 inner face maintained at a temperature of 70 degrees centigrade, outer face at a temperature of 100 degrees centigrade, k equal to 0.58, find Q. What is Q? And the answer you should get, I want you to do this on your own. If you do this problem on your own, the answer you should get is Q is equal to minus 4.37 watts. So, please do this problem, which is an extension of what I just did on your own for a spherical situation. You should get this answer. Mind you, again the negative sign is because heat is flowing radially inwards. That is the reason for the negative sign. All right. Now, we want to introduce the idea of what is called as a thermal resistance. We have got solutions for a few one dimensional steady state situations. Now, we want to introduce the concept of what is called as a thermal resistance. A thermal resistance is defined in a manner very similar to an electrical resistance defined by Ohm's law. Suppose I have, let us look at the right side of this figure. Suppose I have an electrical resistance through which a current I is flowing and across which I have a potential difference delta E. Ohm's law states that the electrical resistance R electrical is equal to delta E divided by I, right. That is Ohm's law. Now, in an analogous manner, I define a quantity called a thermal resistance, and I define it as follows. I say, suppose I have a solid and across the faces of the solid I have a temperature difference T 1 minus T 2. This is similar to the potential difference delta E, and there is a heat flow rate Q flowing across this solid. The Q is analogous to the current I. Then the thermal resistance of the solid is given by the temperature difference T 1 minus T 2 divided by Q. Okay. That is how we define it. We define a thermal resistance as equal to a temperature difference divided by the rate of heat flow. This is the definition of a thermal resistance. Now, immediately I can go back and see the case of the infinite slab. For the infinite slab, what did we have for the, look at the expression for heat flow rate. For an infinite slab, what will be the thermal resistance? With this definition that I just gave you, for an infinite slab, we have just derived the expression Q is equal to K A by B. If you go back in your notes, you will see K A by B into T 1 minus T 2. All right, we just derived that expression. Compare it now, compare this expression with our definition. How do you define thermal resistance? We say thermal resistance is equal to T 1 minus T 2 divided by Q. Therefore, for an infinite slab, thermal resistance would be given by B by K A. All right. That is how we will get the expression for the thermal resistance of an infinite slab. For heat flowing from a surface to a fluid, that is Newton's law of cooling. The thermal resistance, if I again use this definition of T 1 minus T 2 by Q, the thermal resistance would be equal to 1 upon H A by comparing with Newton's law of cooling, this definition. For an infinite hollow cylinder, all right. If I go back to the previous transparency now, for an infinite hollow cylinder, RTH would be given by the logarithm to the base E RO by RI divided by 2 pi K L. So, once I have an expression for heat flow rate and I have a definition for thermal resistance, I can write down what would be the thermal resistance for a given situation. So, we have put it down for the three cases which we have so far studied: an infinite slab, an infinite hollow cylinder, and when heat transfer takes place from a surface to a fluid. These are our expressions for thermal resistance. All right. Now, why do we introduce the concept of a thermal resistance? You will say, well, I mean, what do I get out of it? The main reason is the following. The main reason is, you know that when there are many electrical resistances in series R1, R2, R3, R4, we know very well the total electrical resistance of all those in series is the sum of R1 plus R2 plus R3. So, if I have many electrical resistances in series, the total electrical resistance is the sum of the individual electrical resistances. Similarly, when we have a number of thermal resistances in series, the total thermal resistance is also the sum of the individual thermal resistances. That is why the concept of a thermal resistance is a useful one and we use it. So, let me repeat that sentence because that is a useful sentence. Thermal resistances in series, can be added to obtain the total resistance. When we have many resistances in series, the thermal resistance, total thermal resistance is the sum of the individual thermal resistances. All right. Now, with this backdrop, let us look at a composite situation. A composite situation is one in which we have a number of thermal resistances in series. So, we are now going to look at, instead of a slab, just one slab that we looked at earlier, we are now going to look at an infinite slab which is composite in nature. Look at this figure. We have now a composite slab consisting of three materials with thermal conductivities K1, K2 and K3, all right, and thicknesses B1, B2 and B3. Three slabs attached to each other side by side. The first one is thickness B1, B2, second one B2, third one B3. Their conductivities are K1, K2 and K3. Okay. And let us say on the left side here, the slab is in contact with a fluid at a temperature T1, and on the right side the slab is in contact with a fluid at a temperature T2. And arbitrarily I have said let T1 be greater than T2. If that is the case, heat will flow from the left side to the right side. If the reverse is the case, it will flow in the reverse direction. It does not matter. I have just taken one temperature to be higher than the other. Now, what do we want to do? We want to find an expression for the heat flowing across this slab. Heat will flow like this across this slab, right. I would like to find an expression for the rate at which heat flows across this slab, and I would like to find an expression for the thermal resistance of this composite slab. All right, thermal resistance of this composite slab. That is what I would like to do. For the moment, let us not look at this expression, we will come to it in a moment. This is the composite slab. We want an expression for the heat flowing across it and the thermal resistance of this composite slab. Now, the first thing you recognize is that for analyzing this slab, we need to recognize first of all that there are 5 thermal resistances in the path of the heat flow. What are the 5 thermal resistances in the path of the heat flow? Starting from the left, we have the heat transfer coefficient on the left side, then the thermal resistance associated with the first with conductivity K1, then second, then third, and then finally the thermal resistance associated with the heat transfer coefficient H2 on this face. So, there are 5 thermal resistances in the path of the heat flow, and for each of them, if I first say that the intermediate temperatures are TW1, TW2, TW3 and TW4, all right. So, for across the first thermal resistance, there is a temperature difference T1 minus TW1, which is governed by Newton's law of cooling. Across the next one, TW1 minus TW2, I can use the result for an infinite slab which I just derived a few minutes ago. Same for the second and the third slab, I can use the linear distribution and the heat flow rate result which I got a moment ago. And finally, again for the last thermal resistance where there is a heat transfer coefficient H2, I can use Newton's law of cooling to put down the expression for heat flow rate for the fifth thermal resistance. So, let us do that. What will we get? We will get, starting with the left side again, Q by A, I am now going from left to right, is equal to H1 T1 minus TW1. TW1 is the temperature of the surface on the left side. Then first slab, Q by A is equal to K1 by B1 TW1 minus TW2. Second slab making up the composite situation, K2 by B2 TW2 minus TW3. 3. Third one, Q by A is equal to K 3 by B 3 T W 3 minus T W 4. And finally, the last one, there is a heat transfer coefficient, Q by A is equal to H 2 into T W 4 minus T 2. All right. These are the 5 expressions, and obviously, Q by A is the same for all of them. It is not just symbolic, all these Q by A's have to be equal, because it is a steady state situation, heat flowing from left to right. Now, I can rewrite each of these expressions in terms of a temperature difference alone. So, I can write, say, the first expression as T 1 minus T W 1 is equal to something. I can write the second one, T W 1 minus T W 2 equal to something. All right. All the 5 can be rewritten like this, and then I can add them up. If I add up, notice what is going to happen. The intermediate temperatures T W 1 will cancel, the intermediate temperature T W 2 will cancel, all of them will go, T W 1, T W 2, T W 3, T W 4, all will go. All that I would be left on the left hand side when I add up will be T 1 minus T 2. If I now add up all the 5 expressions, all the intermediate temperatures will go, and I am simply going to get on the left hand side T 1 minus T 2 is equal to something. Let us put that down. What we will get is the following: T 1 minus T 2 is equal to T 1 minus T 2 is equal to Q by A multiplied by 1 by H 1 plus B 1 by K 1 plus B 2 by K 2 plus B 3 by K 3 plus 1 by H 2. All right, that is the expression that I am going to get, and this is my expression now for the heat flow rate across this composite slab consisting of 3 infinite slabs joined together and 2 heat transfer coefficients on the 2 faces. All right, this would be my expression. And now compare this with my definition of thermal resistance for a composite situation. What will it be? The thermal resistance for the composite situation is given by T 1 minus T 2 divided by Q. So, if I take T 1 in this expression that I have derived here, if I take T 1 minus T 2 upon Q to the left hand side, what am I left with on the right hand side? Whatever I am left with on the right hand side will be my expression for the thermal resistance. So, for the composite case, I get the thermal resistance to be the following, which I had shown you earlier. For the composite case, thermal resistance is RTH is equal to 1 upon A into 1 by H 1 plus B 1 by K 1 plus B 2 by K 2 plus B 3 by K 3 plus 1 upon H 2. And this is nothing but the sum of the 5 individual thermal resistances which I have got. The first one is 1 by H 1 A, second one is B 1 by K 1 A, etc. So, we have not only got an expression for the total thermal resistance of this composite case, we also have shown that when thermal resistances come in series, the total thermal resistance is the sum of the individual components. So, we have done that as well. All right. Okay. Now, we also at the same time, while we are on the composite case, I want to define another term for you, and that term is a term called the overall heat transfer coefficient. It is an important term which we use quite a lot in heat transfer. So, I want to define a second term called the overall heat transfer coefficient. I want to define that term for you. The overall heat transfer coefficient, whenever is defined for a situation in which we have more than one thermal resistance, okay, for some composite situation. We say the overall heat transfer coefficient for a composite situation may consist of two thermal resistances, it may consist of 3 or like we did just now 5 thermal resistances. All right. It is defined as follows. We define it as the overall heat transfer coefficient for a composite situation is defined by the following expression. Let me write down here definition. It is defined by the expression Q is equal to U A into T 1 minus T 2. That is a definition of the term which we have called as overall heat transfer coefficient. U is the overall heat transfer coefficient, Q is the rate of heat flow in watts, A is the area across which heat is flowing, and T 1 minus T 2 is the temperature difference at the two extremities of the system across which we wish to define this term overall heat transfer coefficient. All right. That is how we define this term. Now, mind you, if A is a constant, as in the case of the infinite slab, it is well defined, there is no ambiguity. But if on the other hand A is varying, then we need to tell on what area A the quantity U is defined. It is based on some area. So, if A is varying, I will have to tell the area A on which U is defined. If on the other hand there is no ambiguity like in an infinite composite slab, then of course, I do not need to tell anything on what basis U is defined. Now, compare this definition with the expression which we had a moment ago for Q for an infinite slab. What was our expression for Q for an infinite slab? Let me just show that again for a moment. The expression for Q for an infinite slab was the following. We got T 1 minus T 2 is equal to Q upon A into all this. This was our expression from which I can write Q equal to something or the other, right. So, if I compare this expression for Q for a composite infinite composite slab with my definition of an overall heat transfer coefficient, then for an infinite composite slab I can say for an infinite composite slab the expression for overall heat transfer coefficient will be U is equal to 1 upon divided by 1 upon H 1 plus B 1 by K 1 plus B 2 by K 2 plus B 3 by K 3 plus 1 upon H 2. So, what we have done is we have defined a term called overall heat transfer coefficient, and for the infinite composite slab case I have given you what would be the expression for the overall heat transfer coefficient for that case, since we just derived an expression for heat flow rate across an infinite composite slab. Now, let us move on to the thermal resistance of a long hollow composite cylinder. So, instead of a composite slab, now I have a composite cylinder. Let us look at this figure. Here I have a composite cylinder, a long composite cylinder made up of two materials. Thermal conductivity is K 1 and K 2. The inner cylinder has radius R 1 and R 2, the outer cylinder has R 2 and R 3. The inner surface, at the inner surface there is a heat transfer coefficient H I, at the outer surface there is a heat transfer coefficient H O. The fluid inside the tube is at a temperature T I, and on the outside the fluid which is in contact with this surface is at a temperature T O. So, for this case we have 4 thermal resistances. A thermal resistance associated with the heat transfer coefficient H I, a thermal resistance associated with conduction through the first cylinder, then a thermal resistance associated with heat conduction through the second cylinder, and finally, a thermal resistance associated with the heat transfer coefficient H O on the outer surface at radius R 3. Now, we can go through a derivation for this case again in the same manner as we did for an infinite composite slab and derive expressions for Q, what is the rate at which heat flows across this slab, across this composite cylinder, and what is the thermal resistance for this composite cylinder. We can do both that in exactly the same way that I did for this slab. That means, I will take each one of them one by one and say, let the intermediate temperatures be T W 1, T W 2, then I will say T I minus T W 1 is equal to something, T W 1 minus T W 2 is something, T W 2 minus T W 3 is equal to something, and then finally, T W 3 minus T O is equal to something. Add them all up, get rid of the intermediate temperatures, and I will get an expression for Q and for R T H. All right. If we do that, which I want you to do on your own, because it is exactly a repetition of what we did for the infinite slab, you will get the following results. You will get RTH, the thermal resistance for the composite case, is equal to again the sum of the 4 thermal resistances which make up that composite situation. Start with the inner one, 1 upon H A, 1 upon H I into the inner area. What is the inner area? 2 pi R 1 L. L is some length that we are taking for the cylinder. Second, thermal resistance of the first inner cylinder, log to the base E R 2 by R 1 divided by 2 pi K 1 L. Second cylinder, log to the base E R 3 by R 2, 2 pi K 2 L. And finally, the thermal resistance on the outermost face, 1 upon H O into 2 pi R 3 L. That is the total thermal resistance of the composite cylinder. And obviously, if I have an expression for the total thermal resistance, it follows that Q must be equal to the temperature difference from one end to the other, that is from T I to T O, divided by this total thermal resistance. So, that is my expression for Q straight away. All right. Q is given by T I minus T naught divided by this whole R T H out here. I could also, for this case, put down an expression for the overall heat transfer coefficient by comparing with my definition of overall heat transfer coefficient. Suppose I want to base my overall heat transfer coefficient on the inner area, that is on the radius R 1. What would be the area there? On R 1 the radius would be 2 pi R 1 L. So, my U, the overall heat transfer coefficient then based on inner area all right. The definition of U would be Q is equal to U, and since this is U based on the inner area, that is on the radius R 1, I will put a subscript on it U R 1 to indicate that it is based on the radius R 1 multiplied by 2 pi R 1 L, that is the area, multiplied by the temperature difference from the inside to the outside. And what is the temperature difference? T I minus T O. That is my definition of the overall heat transfer coefficient based on the inner radius R 1, where the area would be 2 pi R 1 L. Okay. Therefore, if I use this definition and use my expression for Q for this case, I straight away get 1 upon U R 1 is equal to 1 upon H I plus R 1 by K 1 log to the base E R 2 by R 1, this is the inner cylinder, then R 1 by K 2 log to the base e R3 by R2 plus R1 by R3 1 upon HO. My definition of U can be based even on some other radius. Say for instance, suppose I say based on outer area. All right. What is the outer area? 2 pi R3L. In that case, I will get an expression 1 upon U R3 is equal to, and I want you to write this on your own. Write this expression 1 upon U R3 on your own. Remember, if I use this value of U R3, I must always multiply by 2 pi R3L. If I use this value U R1, I must always multiply by 2 pi R1L in order to get Q. All right. So, now we are ready to stop here today. What have we done today? We have done the following. We have first of all started the topic of conduction, and I said that while studying conduction in solids, we will be primarily concerned, what we have to do is to satisfy the first law of thermodynamics for a closed system, and that too without a work term being involved. We will not have to worry about Newton's second law of motion or the law of conservation of mass, because these would be trivially satisfied. Then we considered two one-dimensional steady state situations. First of all, an infinite slab, then an infinitely long hollow cylinder. For both of them, we got the temperature distribution, we got the heat flow rate. Then we introduced the concept of a thermal resistance, and I said we introduced this concept because thermal resistances in series are additive. We went on then to a composite situation. We considered an infinite composite slab, got an expression for Q and for thermal resistance for an infinite composite slab. We did the same for an infinitely long composite cylinder, and for both of them I also defined a term called as overall heat transfer coefficient, and said we define an overall heat transfer coefficient as Q is equal to U into A into T1 minus T2, where T1 minus T2 are the temperature differences at the two extremes. And for both these cases, the infinite slab and the infinitely long composite cylinder, we got expressions for the overall heat transfer coefficient U for these two geometries, and that is where we have stopped today.